Hello, this is a short presentation for the paper Mind the Edge, Refining Depth Edges in Sparsely Supervised Monocular Depth Estimation in CVPR 2024 by Lior, Aviad Cohen, Erez Yosef, Alexandra and Michael Dinerstein from Samsung Israel Research and Development Center and Tel Aviv University. Please scan the QR code for the code and data. Monocular depth estimation (MDE) methods infer the depth of each pixel in an RGB image. In outdoor scenes, as considered in our paper, the ground truth depth data is solely obtained using LiDAR sensors. Typically, MDE methods are very accurate in most of the scene, but struggle with the localization of depth discontinuities, depth edges, as observed empirically. That is, the separation between different objects is poorly localized. This is mainly due to two reasons. 1. The supervision around depth edges is especially sparse, as measured from ground truth depth maps. 2. In the process of image and LiDAR alignment, there are typically errors that have the largest effect on depth edges. Some applications that use depth are sensitive to errors in the localization of depth edges. For example, in augmented reality applications, when rendering a virtual object to be placed in the scene, the object is required to naturally blend in the scene. This requires the computation of occlusions, which relies on accurate depth edges. Another example for a similar application is data augmentation for training neural networks, where an object is relocated or inserted in some place in the scene. As in augmented reality applications, a successful blending of such an object depends on accurate occlusion computation that depends on accurate depth edges. Generally speaking, MDE methods solve two main tasks. 1. Depth edges detection. That is, they localize the depth edges in the image. 2. Continuous surface depth estimation. That is, they infer the depth of smoothly changing object parts. Our observation. Task 1 is actually relatively easy, but the MDE network mainly focuses on task 2. When we claim that task 1 is relatively easy, we mean that the depth edges that are obtained naturally in the MDE training are far less accurate than directly training to detect depth edges in a separate network. The solution we propose is to encourage the MDE network to also focus on task 1. To do so, we introduce a depth edge loss, which is a binary cross-entropy between a depth edge map derived from the predicted depth map and the depth edge's ground truth. The depth edge map is derived from the spatial gradient magnitude of the predicted depth map. To obtain depth edge probabilities, we shift the spatial gradient magnitude and pass through a sigmoid. The depth edge ground truth is obtained from a dedicated depth edge estimation network that is trained on dense synthetic depth data and inferred on the training real data of the MDE task. The outline of our method is as follows. 1. We first learn how to detect depth edges from a dense synthetic data from the video game GTA. 2. We apply the depth edges network on the training data of the MDE task. 3. Then the MDE is trained with the standard pixel-wise depth loss and the dedicated edge loss, where its ground truth is obtained in step 2. Finally, the resulting MDE network is used solely on RGB images, as any MDE network. We evaluate our method on 3 datasets: Kitty, DDAD, and Synscapes. To evaluate the pixel-wise depth accuracy, we use the common metrics from the literature, such as the absolute relative error, ARE. To evaluate the localization accuracy of the depth edges, we propose a metric, denoted by AUC of edges, from the area of edge detection. To compute the metric, a one-to-one matching between predicted edges and ground truth edges is first computed. For each predicted edge pixel and each ground truth edge pixel, a precision and recall is computed based on the existence of matches. The AUC is the area under this precision recall curve. The AR metric for per-pixel depth estimation evaluation is comparable between our method and the baseline in all evaluated methods. In the AUC metric for depth edges localization, our method is significantly better with relative improvements between 30% and 50%. For boosting depth and gradient fusion, two competing methods, both the AR for per-pixel depth and the AUC for depth edges, is significantly worse than our method. We present qualitative results for the Kitty dataset. Our method, in comparison to the baseline methods, obtains better localized depth edges. In the DDAD dataset, Our method obtains better localized depth edges in comparison to the baseline method, similarly to the case of the kitty dataset. In the baseline method, the depth edges are smeared and suffer from significant artifacts. In our method, the artifacts are significantly reduced. Thank you for listening. Please scan the QR code for our code and data.